Hello, everyone. So good to see everybody. Hopefully you are feeling pretty good about the semester. We are on the downhill slope. And so that feels good for me. Hopefully it feels good for you as well. But in today's lesson, we are going to talk about one of my absolute favorite topics in statistics, and that is regression. So regression is a really powerful tool that allows us to do several things. So it is known as one of the most versatile tools that we can use in quantitative social sciences. So it's really important and it's really foundational. And hopefully you are going to learn a lot from this lesson if you don't already have a strong understanding of regression. So typically we use regression when we have two variables. Of course, we're going to have our independent variable and our dependent variable. And for the most part, we're going to be looking at those two things. And like I mentioned earlier, we can do several things with regression. We can use regression when we want to look at the relationship between two variables. We can also use it to make a prediction, which is, in my opinion, one of the most fun ways to use it. And so we can look at it to see if our independent variable x can make a prediction about our dependent variable. We can also use it to compare two groups. So there's a third reason, but let's take a little break first and let's think about two different examples that we can use for those two. So if we're thinking about x predicting y, or our independent variable predicting our dependent variable, let's think about two different examples. The first example, let's think about fertilizer and plant growth. So our type of fertilizer would be our independent variable. And maybe we want to know if our independent variable, our fertilizer, can predict the growth of a plant. Maybe we want to think about it in terms of studying. So our independent variable would be how many hours we study for something, and our dependent variable would be our grade. And so maybe we want to know, can hours studied predict our grade on a quiz or a test? We could also think about, can this type of fertilizer predict the growth of this plant? In terms of comparing, maybe we want to think about two different styles of studying. Maybe we want to know if this type of studying is better than this type of studying. So then we would say, did this group who used this method perform better on the exam than this group who performed this method? The last way that we can use regression is by thinking about units of change. So we could think about, for every 1 unit of change in x, y is predicted to change by so much. So let's go ahead and delve into these concepts a little bit further. So we are going to do several camera views for this lesson. Sometimes we're going to be here and have a conversation. Sometimes we're going to switch over to the screen where I can do some writing and I'm just going to kind of write some concepts out. And then other times we're going to go to SPSS. But for now, we're going to switch over and we're going to look at some writing. I feel like this concept is really visual and I want to just kind of write it out as the ideas unfold. So I'll meet you over there at that screen in just a second. Okay, let's go ahead and take a trip down memory lane and land us in whenever we were or wherever we were when we took Algebra 1. And we likely learned the equation y equals mx plus b. And with this equation, we are thinking about slopes and intercepts. So we have a slope and we have an intercept. So in our equation, y equals mx plus b, our slope was m and our intercept was b. In statistics, we use something very similar, but we just give it different names. In statistics, we say that y equals our beta with the subscript 1, x plus our beta naught, okay? So a few things. One, our x is going to be our independent variable. And then the second thing is we're still thinking of slope and y-intercept. So our slope is this beta 1, and our intercept is the beta naught. But typically, we actually see it reversed. So remember, the commutative property allows you to switch the order of add-ins, and of course, you're going to get the same answer. So typically, this is actually how you're going to see the equation written in statistics. So our intercept is first, and then our slope is next, and then our independent variable is x. So this is the equation that we are typically going to use. As another reminder, our slope is rise over run, which means that for every 1 unit change in x, there will be a change in y. The next thing that you want to remember is that if our independent variable x is a 0, we're going to end up with the intercept. And that should make sense because any number times 0 is 0. So if we set our x to 0, it's going to cancel that part of the equation out, and we're going to be left with the y-intercept. And that is going to be actually a really important step in some of the things that we're going to do. So as a quick reminder, in high school, we probably learned in algebra y equals mx plus b. That same concept of slopes and intercepts and rise over run of how the function actually works, we also use in statistics. We just call it something different. And typically the equation will look like this. Our y-intercept equals beta naught plus beta 1 times our variable. Now we're going to go ahead and look at an example in SPSS to see how this works out. So we're going to head over there now. So before we actually look at the SPSS, what we're going to do first is look at the actual word problem and take some notes. So our word problem says that a taxi charges a flat fee of $3 for entering the automobile. So we are going to say $3 fee for just entering. Then on top of that, the taxi charges $2 per mile. So next we are going to say $2 per mile. Then it says to write an equation for the total cost of the taxi ride. So thinking back to that equation from high school where we had y equals mx plus b, our equation would look like y equals 2x plus 3. So hopefully this is kind of feeling a little bit familiar. We're just making really subtle changes here. So now we're thinking about this equation, and so I'm going to write that out quickly. And so now what we're going to do is just fill in our equation that we use for statistics and regression. So we're going to say y equals 3 plus 2x. So as a reminder, this is our independent variable. The 2 is the $2 per mile, and then the 3 is that fee you pay just for getting into the vehicle. So if we wanted to know the predicted cost of a 10-mile taxi ride, all we would do is replace the x with the 10 and work it out, and then of course we would end up with $23 as our predicted cost. So now that we are looking at that, let's head over to the SPSS and we'll talk a little bit further with information there. Here is a quick little data set that Dr. Ko provided us with, and we have our miles and our cost. Now, the equation we just did was very simple to work through, but now let's think about it in this way. Different taxis might charge different rates. And so because of that, let's just say that we wanted to know just like a general average of all these different taxis and different rates. And so what we're going to do is we are going to run a regression analysis that will give us an average of all the different taxis and taxis rate. So we can use all of these different data points to help give us that estimate. Let's go ahead and do that now. So I'm going to go up to Analyze, then I'm going to go down to Regression, then I'm going to go over to Linear. Then this box will open up, and of course, the dependent variable is going to be the cost of the total trip. The independent variable is going to be the miles traveled. Then I'm going to click OK. When we get to this table, what we really want to pay attention to is down here where it has our coefficients. When we look at this, we see this understandardized b and constant. So the constant is actually the y-intercept. And as a reminder, that is what the number that we will get when our dependent variable is set to 0. And that 3.530 is the number that we're going to multiply by our x. So let's head over to that piece of paper and let's go ahead and write out some equations, and hopefully it will make more sense over there. Okay, so I'm just starting off by writing this initial equation. So let's just go over all of the terms and what they mean because there's some new symbols here. So we have our y, which is our dependent variable or the outcome variable for observation I. So that's what this little subscript is. Then we have our beta naught, and then plus our beta 1 x with our subscript I. So as a reminder, the x is the independent variable for the observation I. or for the value of I. And then this new term is our error term. And we have to have an error term because if you remember, we looked at that SPSS output and that different taxis charge different rates. And so the cost of a taxi ride might be a little bit more or a little bit less. And because we just want this estimated average based on the data, we are going to have some type of error, and we need to account for that in our equation. So that's where this error term is coming in. The beta naught is our y-intercept, also called the constant. So if you remember back to the SPSS output, the constant was this. And then our beta 1 is the slope. And this also can be called the regression coefficient on x. So now if we are going to write this with the specific example we're looking at, it would look something like this. We would have our cost, and then the subscript I equals beta naught plus b1. And then for x, we're going to just write the word miles, because that's what we're looking at. And then we're going to put our subscript in there plus our error term. So that's what it's going to look like first. The next thing that we need to consider are the symbols we use when we are using a predicted value. And they're actually called little hats. So I'm just back to a blank piece of paper because I want to show you this. And we are going to put hats on these. And that is going to show that we are making a prediction. So these are estimated or predicted values once we have our little hats on there. So now we're going to go back to the other paper and we are going to add our little hats to show that we are going to make a prediction. So let's go ahead and look at that other page. And I'm going to write one more equation. And this time I'm going to say the cost with our subscript, and I'm going to put that little hat above it. And now I'm going to put those values that we found on SPSS. So instead of the beta naught, I'm going to write that 1.37. If you remember, that was the constant that we saw there. Plus 3.53. That was the coefficient that we saw. And we are still going to write miles and the subscript I, because that's our x, is our miles. And now we can just plug in however many miles we want to know. Notice in this equation, we actually drop the error term because we put our little hat over here. So now we know that we're looking at an estimated value, and so we can actually drop the error term. So now we can use this equation to make a prediction. So this is the predicted regression equation is what it's called. And we can make this prediction. Let's just say we want to know the predicted cost of a 20-mile taxi ride. So all we would do is put our cost, and then we have that 1.37 plus that 3.53, and we would multiply that by 20. And then we work everything out using orders of operation, of course, multiplying first and then adding. And we would end up with a total estimated cost of $71.97. Of course, we need to go back and add our little hat so that we know we're talking about a predicted value. So let's go ahead and just recap this really quickly before we look at our next concept. So we're going to go back to this equation. We know we are working with predicted values. So what we would say is that for every additional mile, the total trip cost for a taxi ride would be predicted to increase by 3.53. And we know that it's an increase because of the addition. So regression, just like if you think back about correlation, and we said it could have a positive correlation or a negative correlation, regression is the same way. So it's this increase because we are adding. If this was subtraction, then we would say that for every additional mile, it would decrease. And I think we're going to see that in some later examples. But again, just to reiterate, because we are adding, it would sound like this, that for every additional mile, the total trip cost of a taxi ride would be predicted to increase by $3.53. And the next thing to think about, which we mentioned earlier, is if we set our mile to 0, we would multiply it by this 3.35, which would leave us with our y-intercept. and that would be $1.37. So basically, that if you were just sitting in the taxi and you went 0 miles, the predicted cost just to sit in the taxi would be $1.37. So now that we have that, we are going to transition to binary independent variables. So let's head over to that. So actually, we're going to go ahead and end this video here, and I will make one more video, and in that video, I'll go over the binary independent variables. So I will see you in that video in just a minute.